A very warm good afternoon to everyone present here. I, Ramya, faculty from Department of Chemistry, welcome faculty members, students, research scholars, and all science enthusiasts assembled here for the two-day national webinar on spectroscopy, the fascinating science of structure determination. Let us start today's proceedings invoking Lord's blessing. I request Jerusha to lead us in the prayer.
Oh, wonderful Savior is Jesus, my Lord. Oh, wonderful Savior to me. He hideth my soul in the cleft of the rock, where rivers of pleasure I see. My soul in the cleft of the rock, that shadows a dry, thirsty land. He hideth my life in the depths of His love, and covers me there with His hand, and covers me. With numberless blessings, each moment He grants, and filled with His goodness divine. I sing in my rapture, oh glory to God, for such a Redeemer as mine. He hideth my soul in the cleft of the rock, that shadows a dry, thirsty land. He hideth my life in the depths of His love, and covers me there with His hand, and covers me there with His hand.
Thank you, Jerusha. That was a soulful rendering. Let me start with this quote by the celebrated astrophysicist Garrick Israelian. He once said, "Spectroscopy can probably answer the question that is there anyone out there, or are we alone in this universe?" Spectroscopy forms the cornerstone of our fundamental exploration and knowledge what we have into the structure and dynamics of atoms, molecules, and biological systems. This interplay of light with matter has helped us in understanding of the microscopic world of atoms to the macroscopic world of stars. It has enormous influence in the world in which we live today. As a testament to its significance and relevance, there has been more than 25 Nobel Prizes being awarded to spectroscopy. And we as Indians also stand a chance to feel proud that one of the spectroscopic technique is named after Sir C.V. Raman, famously called Raman Spectroscopy. It is such a happening, vibrant, and dynamic field that the 2014 Nobel Prize in chemistry was conferred for the single molecule super resolved fluorescence spectroscopy. This webinar from our department is an effort to enlighten students about the significance and relevance of this fascinating, thrilling, and investigative science of structure determination. I now invite Ms. Vasavi, Faculty, Department of Chemistry, to welcome and introduce the speaker of the session. But before that, I would like to invite HOD, Department of Chemistry UG, Afia Mary Ma'am, to address the gathering.
Thank you, Ramya. A very good afternoon, one and all. I'm Ms. G. Afia Mary, Head Department of Chemistry, UG. Welcome you all to the Department of Chemistry at St.Ann's College for Women, Hyderabad, which is accredited A+ grade by NAC, College with Potential for Excellence by UGC and ISO certified. The college, which made a humble beginning in 1983 with just 2 programs, 2 rooms and 106 students, is today a huge institution with excellent infrastructure and 3,570 students at the UG and PG level in 30 program options. Department of Chemistry, one of the oldest departments in St.Anne's College, established in the year 1983. Studied with well-trained and extremely motivated faculty, as well as bright graduate students, department constantly strives to maintain a culture of excellence in teaching and learning. Department is privileged to have 16 faculty members with their expertise spanning diverse areas of experimental and theoretical chemistry. I'm even proud to say that we have senior-most faculty with us having more than 30 years of experience. We are committed to educating next generation chemistry students and establishing an inclusive learning atmosphere. Our outstanding laboratories have an exceptional teaching and learning environment. In addition to the undergraduate program, department offers a very vibrant MSc course, and the goal of the program is to guide the students towards a promising career in chemistry ahead. Department also bestows opportunities to its undergraduate students for pursuing internships at private companies so that they can also gain the industry experience. With its motto, Born with the Best, department has been engaged in inculcating and sustaining the spirit of inquiry and scientific temper in its students in its pursuit of excellence. Seminars, conferences, and workshops have become a way of life. It strives to produce empowered and enlightened women who can face the challenge of their future career and work for the development of nation. A very warm welcome to all the participants. Hope you will have a good time with us these 2 days and get benefited by the lectures. Thank you, and over to Ramya.
Thank you so much, Afia ma'am, for your encouraging words. Now I invite Ms. Vasavi, Faculty Department of Chemistry, to welcome and introduce the speaker to the gathering. Over to you, Ms. Vasavi.
Thank you, Ramya. Good afternoon, one and all. I am Vasavi, Department of Chemistry, St.Anne's College. I am very glad to introduce Dr. C.H. Srinivas Reddy, sir. Dr. Chintalapalli Srinivas, currently working as a scientist in Vikram Sarabhai Space Center, ISRO, Thiruvananthapuram, Kerala. His focus area are identification and development of materials for ISRO missions using spectroscopic techniques. His major areas of specialization is NMR spectroscopy. He had schooling in Jawahar Navodaya Vidyalaya, Choppadandi, Karimnagar, undergraduate studies at Vivekananda Degree College, Karimnagar, affiliated to Kakati University, and masters in organic chemistry from the Usmania University. He did his PhD in IIT Delhi from 2007 to 13, where he is specialized in liquid state NMR spectroscopy. During his PhD, he got an opportunity to do 4 months internship at EPFL, Switzerland, as a part of IIT Delhi EPFL Switzerland MOU. During this time, his work got published in Physical Review letters for the development of pulse sequence to get the chemical shift and coupling information in a coupled spin system in highly inhomogeneous magnetic fields, which got selected as cover page of this issue. Further, he got a postdoctoral position in the same lab at EPFL Switzerland, where he worked from 2013 to 14 in solid-state NMR spectroscopy. Later, he worked as assistant professor on contract base in Department of Chemistry, Central University of Karnataka, Gulbarga from 2014 to 15. During this period, he taught thermodynamics, chemical kinetics to undergraduate students, chemical kinetics, quantum chemistry, and NMR spectroscopy to postgraduate students. Later, he moved to ISRO from 2016 onwards. He has 15 international publications and 1 patent to his credit. Welcoming you, sir. Please take over the section, Srinivas sir.
Okay, thank you, Vasavi, for your kind words. So, I'm sharing the screen. Can you see it? No?
Yes, sir, we can
Yes,
see.
sir.
Okay, here I'll be dealing with the applications of spectroscopy for space science and technology. So, as you know, I think as per my understanding, all of you know about the spectroscopy. I won't build into the much of the introduction of the spectroscopy. As all of you are aware that the interaction of the radiation with the analyte will give you either it can interact with the molecule, or it can absorb with the molecule, or it can re-emit, or it can be scattered depending on the interaction of the uh, radiation with the molecule and means the system under the study. Different spectroscopic techniques are evolved. Let us say that for if it is absorbed, it could be NMR, IR, visible. If it is re-emitted, fluorescence emission spectroscopy. If it is scattered, Raman spectroscopy. Where spectroscopy is coming to handy in our application is that it could be useful for the material characterization. If you know if you have an unknown material, how do we identify any material that we are using? Or if you want to develop any material, how spectroscopy is handy for I means developing that material also. It could be mostly useful, as well as if you already have a developed material and it will be if it is inducted in the space. Let us say that if it is a material used for a launch vehicle or a satellite, it will be having particular conditions. Whether all those criteria is meeting or not, it will be useful for quality control also. As well as if you want to find out any, if your spectrometer is going to the space, and if it is identifying, it can be intended for identification of the molecules that are, let us say that in the atmosphere, let us say Mars or Moon, what are the elements are present for future exploration. It can be also useful. Here I have not covered failure investigation analysis also, because if particular component is failing, how spectroscopy can be useful also can be dealt. But as it is a more of our within ISRO, so we are not divulging that information, but that can be used there also. So here is a major, this is the workhorse, that is a Polar satellite launch vehicle. This is the workhorse for most of our ISRO machines, where even our Mars Orbiter mission and Chandrayaan-1 and Chandrayaan-2 also were carried out by this PSLV mission, PSLV launch vehicle. What is the launch vehicle by default? So it will take some payload. That means it could be any satellite or it could be anything to the desired orbits. So that for that launch vehicle is used. This Polar satellite launch vehicle will be having 4 stages. So these 4 stages will be alternate solid and liquid stages. So this the down stage, first stage is solid stage, second stage is liquid stage, third stage is solid stage, and as well as fourth stage is liquid stage. So alternate solid and liquid stages will be there. So here we are showing where our materials are used and how we will be deciphering which type of material is qualifying for this launch vehicle. We will be dealing here now. As I am working in VSSC, I will be mostly dwelling upon the launch vehicle systems only. So here if we see that, so what is the launch vehicle? Basically structures will be there for the launch vehicle, as well as the propellant will be there. So here the first stage is a solid state, solid based propellant, where it is used as a hydroxy terminated polybutadiene is used as a binder. So in the solid state, actually by default, what is required for anything to move further? So you have to apply a downward force so that it can move up. So what is the force it is required? How can it attain is that by use of propellant. In case of normal, our cars or bikes, we need only fuel, because we don't need any oxidizer, because already our air is having a plenty of oxygen, so we don't need any oxidizer. But in case of rocket, after some atmosphere, you won't be finding any oxygen. So that's why, so the basic components of any propellant will be the fuel and oxidizer will be there. Whereas in case of solid propellant, you cannot mix it properly. That's why you will be having a binder that can mix the oxidizer as well as the fuel in a proper ratios, so that it can be homogeneous, so that the burning will be continuously. We can easily monitor the burning if it is homogeneous. So that's why this hydroxy terminated polybutadiene based binder will be used to bind the here solid state. We will be having a aluminum fuel as a fuel as well and ammonium perchlorate as the oxidizer. So these two things will be bind by the hydroxy terminated based propellant. So spectroscopy will be handy. How it will be handy? We will be dead late in the following sections. So as well as this STPB, you will be having an ambi-link as a cross-linker. That means to cross-link this STPB will be a linear polymer. To cross-link this one to have a better binding capability, you will be having an ambi-link as a cross-linker. We will be seeing what is ambi-link and how it can be used. The next stage is in the solid stage only. You can see that. So the throat, below there is a throat where you will be having a highly flammable gases with high temperature will be flowing out so that rocket can propel upward. So here you need to have a better ablative material. What is ablative material? It will sacrifice it itself, but it won't make damage. So while the propellant is coming out, so it will protect the structural system to be intact so that there won't be any harmfulness to the this throat. That's why here carbon phenolic composite will be used as a ablative material, whereas in the liquid state silica phenolic composite material is used as a nozzle liner material so that it can protect the nozzle from the high temperature gases flowing. Whereas for any structure to protect, if high load propellant is burning inside, that means the structure can be damaged. To prevent the damage, rubber based insulation system, it could be nitrile based or EPDM based insulation system is used. Whereas to bond this insulation system to the propellant, you should have a suitable liner. For that, STPB based liner will be used where it will be higher in the isocyanate content so that it can probably easily bind to this insulation material as well as the propellant. If you go to the top, so here in the third stage, it's a Kevlar reinforced epoxy based composite motor case is used, because here first two stages you can have alloys, because in the first two stages you don't have any, you need not to worry about the weight of the vehicle. As you go up, so if you increase the weight of the vehicle, you will be adding cost to the vehicle. Why? Because then the payload capability will be reducing. If your weight of the vehicle is higher in the upper stage, then your payload capability, that means to carry the satellite or any system you want to study and in the space, that can be reduced. That's why you have to use a low weight system in the upper stage when you go to the upper stage. Instead of alloy, so you'll be using a Kevlar reinforced epoxy based composite motor case as a structural material for the third stage. Even whereas for fourth stage, you will be using low weight alloy, which is based on the titanium columbium alloy will be used in the fourth stage. If you go to the top, there will be a payload fairing. So all this payload fairing, and from top to bottom, you will be having a thermal protection system, which is based on the silicon polymer. So that can be protected. That will protect the outside vibrational and as well as thermal and pressure loads from. It will protect the structure of the launch vehicle. Whereas if you see the satellite, it will be having a. If you deploy any satellite to work it continuously, it requires power. How it can take power from here? From the space, only the basis of power is the solar radiation. So you will be having a solar panels. For that, you have to bond that solar cells to the structure. For this, different types of adhesives are used. So in all these launch vehicles, you will be having different types of adhesives that can be used to bond the metal to metal bonding or metal to rubber bonding or rubber, polymer to polymer bonding. Different types of rubbers also used. For that also spectroscopy is used to decipher how to qualify the rubber, or if any issue is there, what is the issue with the rubber also can be found out. Similarly, if any launch vehicle is going up, that means you will be having different vibration loads will be there. To protect that vibration loads, you will be having a silicone based vibration system isolators will be there that will protect the launch vehicle and the satellite from the surrounding systems. So if you will discuss some of these things in the how spectroscopy is used to dealt to find out these structures. Let us say that this phenol formaldehyde, I told that this nozzle, to protect the nozzle from the high effluent gases, you will be protecting the nozzle with carbon phenolic resin or silica phenolic resin. Then how do you identify how do you qualify this resin? So this is the basic structure of the resin, where it will be having a aromatic moiety and methylene bridges as well as the methyl groups. So here in that, so in your proton number, you will be having three different regions. One will be in between 6 to 8, it will come the aromatic hydrogens. In between 4 to 5, methyl hydrogens. In between 3 to 4, bridged hydrogens you will get. So from these three types of hydrogens, you can integrate these three hydrogens and find out what is the quantity. It means what is the amount of aromaticity and what is the amount of methyl groups and what is the amount of methylene bridges, from which you can find out what is the basic structure of the phenol formaldehyde resin. So we will be having, already we have a qualified phenolic resin for both the carbon phenolic composite as well as silica phenolic composite. So whether by using these integrals, whether all these criteria is matching or not, we will be checking. So in addition to this, there will be different other criteria also. What would be the moisture content, or what should be the phenol content, and what should be the formaldehyde content in the phenol formaldehyde resin after the reaction will be there. But how the spectroscopy used here is that to find out the structure and number average molecular weight of this particular phenol formaldehyde resin can be qualified. When you go to the hydroxy terminated polybutadiene, I told that you will be having this will be used as a binder to bind the fuel as well as the oxidizer, so that it can be used for the solid state as it will be used as a solid state propellant. So what is the basic microstructure of hydroxy terminated polybutadiene is that you know that polybutadiene will be having a conjugation. It's not a continuous conjugation. You will be having a olefinic functional group as well as a OH functional group. How this olefinic backbone will be? It could be either cis way, or it could be trans, or it could be vinyl. So by this finding out this cis, trans and vinyl content, it could be easily done by infrared spectroscopy, by which you will be knowing that how well this STPB is arranged. If it is more trans, means it will be orderly arranged. If it is cis or vinyl, means that orderness will be lagged. So you will be having a particular ratio of cis, trans, vinyl, where trans will be having around 60% and cis and vinyl will be having around 40%. So that this is also, we have already specification is met. So whether it is meeting that specification or not, we will be checking with the infrared spectroscopy to find out what is the cis, trans and vinyl content. If you go to the hydroxy terminated end group, it will be having three types of hydroxy terminated. It could be geranyl, where it will be having a branching with this CH2OH functional group, or it could be a linear functional group where it will be a linear with termination as OH, whereas this will be having a vinyl will be in the end, whereas the here structure in this one, it will be in the chain, whereas in the vinyl thing, it will be in the end with CH2OH as the end. So here these two are chain extenders, whereas geranyl is a branching thing. So how this can be used? What is the requirement of this hydroxyl end group means? How automatically just HTPB cannot be used as a binder. It should have a NCO so that it can cross-link and go further. That means there will be a urethane linkage it requires to form, so that let us say that this is a hydroxy terminated polybutadiene, which will be reacting with a toluene diisocyanate or MDI, by which urethane linkages will be formed. So that this will be having a cross-linking network by which whatever this will be mixed with the propellant, that is fuel as well as the oxidizer, so that it will be having a proper homogeneity. It will bind that complete oxidizer and as well as the propellant. So to know how this reaction is happening, propagating, you should have a particular amount of geranyl, particular amount of hexenol, particular amount of vinyl in your binder. So in this case, you will be having a C13 NMR spectroscopy, where you will be finding this CH2OH will be coming between 50 to 70 region, where you can distinguish geranyl, hexenol and vinyl with its chemical shift variation. by which you can find out the intensity as a function of this chemical shift will give you the percentage of geranyl, percentage of hexenol, and percentage of vinyl. So whether this will be in particular specification, whether it is meeting the specification or not, we will be getting by the 13C NMR spectroscopy. So as well as we are going with the, as I told you that it requires a cross-linker for which we will be using a, this is a cross-link system. It's not a single OH. Here it's a diol, whereas it is a triol. So this will be used to cross-link the STBB so that it can have a cross-linking system when you react with the TDI to have a urethane linkage, so that you can have a proper binding with the propellant. This also can be quantified, and whether it is meeting the spec or not, you can understand. So now, as you know that propellant systems are different types will be there. Now in the PSLV we will be having a solid stage as well as the liquid stage, where both are in the liquid state. Liquid state propellant you will be having both the liquids are in the room temperature liquids only. Whereas in the cryogenic and semi-cryogenic stage you will be having a kerosene as well as a liquid oxygen as a propellant. So this it is under development. So where this will be having a better thrust and specific impulse, so that with less weight only you can achieve maximum distance. That's why this is also under development. So what is the problem? We cannot directly use the kerosene. What is the problem with the kerosene is that you will be having, if you see this one, 0 to 8 ppm, 0 to 4 ppm is the aliphatic region, and 6 to 8 ppm is the aromatic region. So if you are having a higher aromatic content, while burning the propellant, you will be having the gases will be exhausted. While the gases will be exhausted, the nozzle will be choked with these aromatic things, because aromatic things will form, aromatic functional groups will form a layer, so that there won't be proper evolution of the propellant exhaust fumes. So that's why you should have a stringent criteria that you should have as much less as aromatics are possible. So for that one, istrocin is developed, where you will be having, you will be hydrolyzing your this kerosene, so that you should have a lesser aromatic content, so that it would be qualified for the semi-cryogenic stage, where istrocin means that is the aromatic less kerosene can be used as a fuel, and the liquid oxygen is used as an oxidizer. So as I told you that different types of adhesives used for different types of launch vehicle subsystems, where I told you that solar cell adhesive is used for the to bond the solar cell to the satellite. How it will be bonded means the solar cell adhesive is a silicon based adhesive, where you will be having a particular element of phenyl, vinyl, and methyl groups, by which you can form a this is one of the part A system, where part B will be having a hydride functionality, so that this hydride SiH system will cross link with Si vinyl system to have a particular resin which can be used for as an adhesive system. This is one of the part system I'm telling. So here, if you are going for, these are a launch vehicles. So if you are going for the high temperature application, you may need to go for ceramic matrix composites, where it can withstand higher temperatures. Now we are aiming for Gaganyaan and reusable launch vehicle, where the launch vehicle will go up and it should come back. So where it has to withstand high temperatures and pressures and harsh environments. For that, you have to use ceramic matrix composites as well as other composites which will be withstanding the more temperature more than 1000 degrees, 2000 degrees centigrade. For that, here we have developed and analyzed this ceramic system, where here if you see that this is a vinyl triethoxysilane, when it is reacting with S3PO3 at a temperature of 80 to 90 degrees centigrade, where it will be forming a polymer. This polymer so this ratio will be varying, where 1:1 ratio, 1:2 ratio, and 1:1 ratio, where you can see A, B, C. You see that this 1:2 is BSIV1. This is this one A, and this is 1:1, 1.5 and 1:2 ratio. We will be varying this hydroboric acid with vinyl triethoxysilane and formulating a polymer. This polymer on heat treatment, different heat treatment will be done at 900 degrees. If you see the 3 spectrum, In the left side, if you see that 900 degrees centigrade, 1500 degrees centigrade, and 1650 degrees centigrade, you will be heating this polymer. So you will be analyzing. Actually, you here to withstand high temperatures, we need a silicon carbide system, which can withstand a high temperatures, more than 2000 degrees centigrade. Where this SiC is evolving, if you are heat treating this polymer, if you see that at 900 degrees centigrade, still this SiC formation is not there in all the three cases. Where at 1500 degrees heat treatment, where the initial beta silicon carbide formation is there in all the three systems, but still SiO4 phase is there in the second heat treatment. Where when you go for 1650 degrees centigrade heat treatment, you will be having all the three, means in all the three systems, alpha and beta silicon carbide are evolved. Whereas if you see in the FTIR spectroscopy also, this around 1000 region is of SiO-Si linkage, where if you see around 830 region is of SiC formation. So around 900 degrees, almost its formation is very less. If you go further, both SiO and SiC are there. Here, if you see the second from bottom second spectra, if you see 1090 and 827 are there. That means it exists as both SiO and SiC coexistence is there. If you further heat treatment to 1650 degrees centigrade, complete formation of silicon carbide can be seen in IR spectrum also. Where in the three systems you can see all evolution from SiO to SiC phase. If you go to the Raman spectrum also, if you see that these are D and G bonds. But if you go to this left side, 778 and 941, these are of SiC formation, where you can see that here we have shown that already we know that there is no formation of SiC in the 900. Here we are showing below one is 5100, above one is a 1650, where there is a occurrence of SiC, even you can find out from the Raman spectrum. So all this spectroscopy will show that the SiC formation is evolving initiated at 1500 degrees centigrade, which will be completely converted into 1650 degree heat treatment for this polymer. So in your case, as I told you that a rocket will be having different stages, and each and every stage different O-rings will be used to have a better tightness. Mostly these O-rings will be used as a perfluoropolymers will be used. So how to understand the nature of these perfluoropolymers, whether it is CF2 based or if it is CF2CH3, which type of polymer systems is used, that we can find out from solid state NMR spectroscopy. How solid state NMR? Because these samples are not soluble in any of the solvents. So you cannot identify using a normal or liquid state NMR spectroscopy. In DCMS, you can find out what is the type of species, but you cannot find out exactly what is the quantitative nature of the these species. So the handy is the solid state NMR spectroscopy, where you will be filling the sample, where here you don't need to have any solvent is required. Here no solvent is required for the observation of this system. But what you have to do is you have to spin with the highest spinning speeds. What is the advantage with the highest spinning speed? Means if you are having a liquid state NMR, your sample you will be dissolving in any particular solvent, so that the dipole interaction between the, let us say that some system, let us say that is ethanol is there, CH3CH2OH. Each and every molecule of CH3CH2OH will interact with each other, so that you will be having a dipole interaction with one particular molecule with the another part. So they do talk each other. To avoid this talking, if you are having a liquid, due to Brownian motion, they will be tumbling of these CH3CH2OH all over the solution, so that there will be net dipole movement, net dipole interaction will be zero. Then you will be having a only scalar coupled interaction you can see in the any particular system. Here, if you are having a CH3CH2OH, you will be having a CH3CH2OH. You will be having a 3 different peaks with based on their chemical environment. You will be having a 3 different peaks. So, but if you are doing the same CH2OH in a solid state NMR, due to the interaction between the nuclei, you will be having a one single broad peak where you cannot identify which type of spin system it is. For that, you have to spin the nuclei with higher spinning speeds. Depending on the nature of the system, you can increase the spinning speed. Let us say that this is the left side is CF2 system. By increasing the spin speed, here if you see that on the top system, around 120 ppm and 100 ppm, you think that these are the peaks. If you are spinning with 5 kilohertz, but if you increase the spinning speed, you can see that you will be having a single system. This is C13 CPNMR, where you will be having a single peak. This is corresponds to CF2 system. So that means based on the system, you can increase the spinning speed and find out whether it is of single chemical system or if you are having a different types of systems. Right side here, you can see that if even at higher spinning speeds, you will be having different chemical shields. That means it's not a single system. It will be having a multiple spin systems are in that particular O-ring you can find out. So here we have done C13 NMR of perfluoroelastomer that are used in our launch vehicle. So here we have found that this system is composed of tetrafluoroethylene and this oxyfluoro, this trifluoroethylene. Where here you can see that these three different peaks you can find out, from which you can find out what is the M and what is the N repeating unit. By deconvoluting this each peak, you can find out what is the ratio of these peaks also. So that in this case, in our O-ring, this kind of spin system is there. Means the CF2 system is this much and other system is this much. You can find out what is the ratios of those systems that we are using. Because sometimes in this launch vehicle system, here some things are indigenously prepared. Some systems, some chemicals we are procuring. At some point, there is a possibility that the vendor may deny supplying that chemical. So our main focus is to indigenize all the systems that will be used in our launch vehicle. That's why whatever the systems we are using, we are capable to indigenously prepare all those systems, so that we should not rely on the third party, whether it could be an Indian party or it could be mostly foreign party. Sometimes there is a possible, there will be clashes, so that particular supplier may not give us that particular chemical, so that then there should not be any issue in flying the launch vehicle. So that we will be most of the cases we will be developing all the materials, we will be analyzing and developing all the materials. So this is another system where, so this is the particular component. So this is organic residue from Murcian meteorite which got hit in Austria, place in Austria. That's why that place name is Murcian. So that's why it is named after that place. So that meteorite hit the that our planet Earth. So those fragments were collected to know what is the life outside, whether any organic residue that we will get from that particular component. We have analyzed, this has been done by the NASA. So where they have found out that what is that organic residue is there in that particular this meteorite fragment. So here we can easily see that it has different aliphatic groups as well as carbonyl group is there, as well as this in between is the higher one is the aromatic entity. So it will be having this organic residue also you can find out. So here we know that our launch vehicle as well as in the satellite we will be using so the indigenously developed lithium batteries are used. So these lithium batteries, what is the composition and structure and the ionic transport mechanism also can be found out with different spectroscopic techniques. So here this fuel cells also will be used for long duration machines, where the water will be used as a medium, where H2 and O2 will be combined to form, where in between these two cells, this membrane, proton exchange membrane will be used. Here this proton exchange membrane will be different types of proton exchange membranes are there. Here this polyether ketone by sulfonation will be having a protonation this thing. So this, what is the activation energy of this deprotonation and this proton transfer will be found out by solid state NMR spectroscopy. So you should have a lowest activation energy to have a better proton transfer, by which you can have a better efficiency of the particular system. So this is a particular rubber used in particular system where we don't know what is the composition of the material. By using the PYGCMS, we can find out that this is the fragments are of chloropin. That means this corresponds to a neoprene rubber. So what is the advantage of PY-GCMS over GCMS? GCMS you cannot do the polymeric material because you will be the GC column will be trapped with this polymeric material, so which will be difficult to get off. So that's why you will be pyrolizing the. So here this pyrolysis GCMS mostly used for the polymer samples, where you will be pyrolizing that particular polymer, which will be went through this GC column, followed where the columns will be separated with respect to a retention time of that particular species. Here you can see that at 2.06 minutes, this is a major thing. This, if you are clicking this here, you will get the mass spectrum. So this corresponds to the major M by Z EIT at peak. This corresponds to the our chloropene. So that means this particular fragment corresponds to the neoprene rubber. That's how we will find out what is the rubber used in particular system. If you are not having any clue about the particular system, we'll be doing in this way. So if you want to quantify, if you are having multiple spin systems, how do you quantify that? So that means first of all you will be doing a IR spectroscopy to know what are the functional groups that are present. Then you will be going through the GCMS or pyrolysis GCMS spectroscopy, where you will be having what are the components based on their M by Z ratio. Here we found out from the GCMS that actually here this is a system where NiAl and Freon as used as a solvent, that we want to replace that Freon solvent with the water HDG solvent. So that this water HDG is a indigenously prepared system, where whether this water HDG system, whether it is compatible with this NiAl or not, we want to know. What is the NiAl? It is a hydrocarbon. So this water HDG, where if you are adding this diluent, whether it is giving a clear solution or not, we want to know. But the particular group, they told that it is forming an emulsion. So they have given the sample to us to find out why it is happening. So we have found out that by using IR and GCMS, we found out that what is the functional group and what are the fragments, from which we have found out that water HDG of 3-component system. This is a dichloroethylene, and the other one is decafluoro. This is a decafluoropentane. This is right side top one, and in the middle one is heptafluorocyclopentane. So these 3 components are present in the water HDG. After mixing, what is happening? So we have overlaid this below one is the NiAl, which is right side is the hydrocarbon. I told that this NiAl is based upon the aliphatic hydrocarbon. This right side. Left side is these 3 components that I told you. So after mixing, what is happening means, if you see here, this right side, this water HDG as well as decafluoropentane, when you compare with the below spectrum, they are depleting. That means after mixing, they are mixing in such a way so that there is evaporation of 2 of the solvents, so that there is no proper compatibility with this NiAl. Then we check with the literature what is the cause of that one. Means this dichloroethene and decafluoropentane having low boiling point then compared to the cyclic system. That's why they are evaporating. So this input we have given to the particular group, so that in this way they can identify that what is the mixing, at which temperature they have to mix these 2 systems. Like that they can find out with our inputs also. So as I told you that different composite materials could be used for the different systems. So here for making a composite, they need a mold. So this mold, the component actually they used to procure from outside. So this also we want to indigenize at our VSS. For that they have given this sample to us to identify what are the components in that mold. So this is a 2-part system, out of which we have found out that one of the part is, so this 3-component system from IR and NM, IR from GCMS, from which you will be knowing, from GCMS you will be knowing the fragments, from IR you will be knowing the functional groups, by which we have found out that it's a cyclohexane diamine isomer and diethyl toluene diisomer and bisphenol A. So you will be having these 3 components. Using from NMR integrals, you find out what are the ratios of these 3 systems, from which you can indigenously prepare this mold also. So all the spectroscopy like the IR and GCMS or NMR, these three are the basic techniques to find out any unknown material, or if known material is there, what is the composition of those chemicals. Similarly, this as I told you that different adhesives is used. As I told you that these adhesives could be based on epoxy or phenolic based adhesives. So here this adhesive, they want to know what is the type of adhesive and what is the plasticizer used in this. So here from GCMS we found that this is a from IR spectra assignment we found that this is the epoxy based adhesive, and from GCMS we found out that these two are these two fragments we have found out. One is the DGBA, that is diglyceryl ether of bisphenol A. Other one is a diethyl phthalates. This diethyl phthalate is used as a plasticizer in that particular adhesive to reduce the friction and to have a easy flow in nature, so that it can be easily used as a adhesive. So these two we have found out, and from NMR we have identified what is the percentage of these two components. So if you, as I told you that basic research also spectroscopy can be used. Here how it will be used is that, so here alkane is used as a cathode material for lithium batteries. So how the lithiation is taking place can be known from the proton and C13 NMR. If you are lithiating it, where it is attacking. So if you see the C13 NMR, from below you can see that C13 NMR before and after. Above one is before and after C13 DEPT Dept 135 NMR spectrum. From Dept 135, what do you know is that whether it is a CH or CH3 or CH2 or whether it is having any attached protons or not, you will be knowing. From here you can see that from 140 to 200, these in Dept 135 they don't have any protons. So that means either it could be due to carbonyl or it could be due to the carbon attached to oxygen, or it could be ring moiety. But if it is more than 140, only two possibilities are either it could be attached to oxygen or it should be carbonyl. But if you see that from before and after, you see that from 140 to 160 region, you see complete displacement in the peaks. Whereas in 180 to 200, only one peak is too much displaced, whereas other peak is not much displaced. That means there is not much lithiation is happening here. The lithiation is that is happening is to this 2OH and to this carbonyl, by which you can understand mechanism and write a mechanism that so lithium is happening here as well as it is forming a 6-member ring here, but it is not attacking here. So identification of any contamination is there. So if you are running any test, if some impurities you can see in particular chamber, you will be taking that material and finding out what is the component, what is the cause of that contamination. Because if you are testing one thing and some failure is there in a initial trial, at this point of time you should identify what is the cause of that contamination. So here pyrolysis GCMS of such contaminant is brought to us. So we found out that it is based on the this pyrolysis GCMS. We found out that it is based on the phthalates and some oil that is used. So this is the aliphatic hydrocarbon. Mostly it's based on a particular oil that might have gone to the chamber that leads to the contamination. Also we could find out. So if you see that this is a cryo upper stage, which is used for the GSLE Mark III vehicle, where this cryogenic upper stage will be when they have done the heat trial test. Here right side you see that some white colored deposits they have found. They want to know what is the type of deposits from IR and SEM EDS, that is energy dispersive spectroscopy. From IR you can find out that. So it's based on the around 1000 and 1400. You can find out that it's based on the silicate and carbonates. But it is which type of silicate and carbonates you can find out from SEM EDS, where you will be having a elemental spectra, which is based on the which silicate and carbonate. Here you can see that magnesium, calcium, and aluminum are there. So it's based on the silicates are based on magnesium, calcium, aluminum. Those might have used in particular component that is depositing here. So these are the what we have discussed up to a launch vehicle with different types of materials that are used and how to identify them. If any unknown material is there, how to identify them. If known material is there, how to quantify them, how to give the quality clearance for these things. We have studied now. We have seen it till now. Now we will be going to the spectroscopic methods to study the planetary atmospheres. how the planetary atmosphere can be studied is that either we have to send the spacecraft to the particular planet or its environmental system, or we have to launch that spacecraft on the planet. So to realize this one, it will take at least 10 years, because from the idea to conceptualization, it will take at least 10 years. So other way is that Earth orbit and ground-based observations also there. That means you won't be taking your system or spectrometer till the particular planet, but you will be taking outside the Earth atmosphere, so that you won't be having these atmospheric interferences in detecting the any spectrum. That means whatever the light, solar light is emitted by that particular material, you can observe by that particular spectrometer by orbiting through the Earth, so that you can eliminate our Earth interference, atmospheric interference. The other one is ground-based observations. In this ground-based observation, you will be placing the spectrometer down only. From the emittance of the solar radiation, you will be finding out what is the particular component that is reason for that particular irradiation. So, but what is the advantage of the spacecraft is that you can observe that particular planet in situ, so that you will be having a better advantage of, but you won't be having any terrestrial atmospheric interference. But on the other hand, they are expensive, because you have to take this satellite till there. So that means you should have a lesser mass, and you should have a power consumption. All these things will be taken consideration, so that your properties are moderate. You won't, like what we are using ground based, you can't use like some 2 tons, 3 tons. You cannot directly take one spectrometer and you won't launch there. So you will be having a compact size, so that you can have moderate observation, but you will be having a better clarity on this observation. So you will be having a restricted mass and size and power consumption and moderate properties, but you will be having a better understanding of particular planet. But whereas for Earth orbiting observations, where you will be observing the stars, galaxies, and nebulae, so you need not to go there, but your servicing is easy. That means if some particular spectrometer, if you are taking to the Mars or Moon and placing there, if some issues is there in connectivity issues or spectrometric issues are there, you cannot go back and do that rectification. Then once it is placed, means however the results it is giving, that is the final, means you have to take that results only. But if you are Earth orbiting observation, that means you'll be placing particular component. Let us say that Hubble telescope is there. So you have placed in the lower Earth orbit. So this is around 500 kilometers from the Earth. If any issues are there, you can easily reach there and you can do the rectification of that particular thing. Like that in Hubble telescope already happened also. If some issues are there, it was launched so many years back, 20 years back. Still, you can able to rectify if any issues are there, that can be replaced and that can be done. So that is the advantage of the Earth orbiting observations, where you can replace a certain thing if anything is defective. But if you go to ground-based observation, you need not to have any kind of things. So you can be lavishly having. You won't be having any limit to the mass and size. But the only issue is that there will be background issues will be there. Where you won't be having a clarity on that particular species. Let us say that here oxygen, carbon dioxide, methane, and water, they have observed. This is a NASA-based infrared telescope facility. So where they have observed, but what is the percentage of that one? You won't be having that much clarity. You can say that these are the species are present. You can't tell the quantitative nature of those species. So what are then you have to go for the payloads. That means you have to land that particular spectrometer there. Then you have to study, or either it could be landed on that particular planet, or it can revolve on that planet, so that you can understand its atmospheric as well as soil nature. So different types of spectrometers are used in Mars and lunar missions. So I won't be dwelling too much all the spectrometers, but here I am listing out the spectrometers that they are used in the Mars and the lunar missions. So Mars spectrometer is widely used, XRF is widely used, and UV, IR are widely used spectrometers. So alpha X-ray spectrometer also is being used to find out the elemental composition of the particular that atmosphere or the soil. So if you go to the alpha X-ray spectrometer, what it does is that it analyzes the elemental composition of the sample. So that means you will be irradiating with alpha and X-rays. So with the scattered X-rays, you will be finding out what are the elements are present. So, but this kind of system is easy to find out the lightweight elements. But if you want to go for heavier elements, you have to go for the X-ray fluorescence. That means it will be having two components. One is the this is alpha particle will be if you are irradiating with alpha particle, whatever the knockout electron you will be absorbing by X-ray. So that is called as alpha particle induced X-ray emission. Other one is X-ray fluorescence. That means you will be irradiating with X-ray, and whatever the knockout electron you will be finding out. This is the XRF. So with these two we have done with the Chandrayaan 2 rover, but actually unfortunately we could able to the rover got an issue, but whatever only the satellite could able to place there, but this rover we had an issue while landing. So whereas this APX spectrometer in Mars, here NASA has launched Mars Pathfinder, where the Sojourner has this APX spectrometer, where it found out what is the soil type. So what are the rocks? What is that rocks are possible? Means what are the elements composition of the rocks they have found out using this APX spectrometer. As we know that this mass spectrometer, we cannot go with the whatever the mass spectrometer that are available here in the ground state, because we cannot. There is a mass limitation as well as some size limitation. So the basic things that mass gives is the source, analyzer, and detector. Mostly will be all the machines that used till now. The detector used, analyzer used is a quadrupolar analyzer is used, because it will be withstanding higher harsh environments also. Because once it is placed there, there will be having a harsh environment, so it should withstand those environments. So that's why quadruple ion analyzer is used. So in our Chandrayaan, we have used even both for Chandrayaan 1 and Chandrayaan 2, and for mission Mars orbiter mission, we have used a mass spectrometer. So in these three cases, whereas Chandrayaan 1, we have used a moon impact probe, where we will be finding out while it is entering the atmosphere of the moon. So while it is descending phase from 100 kilometers, it will find out what are the elements are present in the atmosphere from 100 kilometers down till it hit the moon. So this is a moon impact probe. In that this Chandra's altitudinal composition explorer 1 is placed. So they have found here, we have found that this it contains direct evidence. So this is the first observation we found out that direct evidence of water is found out. So we found out that CO2 is dominant in the sunlit lunar atmosphere, and we found out that argon also is present in a smaller quantities, and trace quantities of higher mass numbers also present we have found. Other than this mass spectrometer, moon mineralogy mapper as well as near-Earth imaging spectrometer also used. We have found that lunar silicates also found, which is interacting with the oxygen to form silicates. So here we have, as I told you, that from top to bottom when it is descending, so they will be having an altitude variation. From altitude, what is the vapors, water vapors that are evolving that this chase one has detected as a function of altitude, where different altitudes you have a different mass profile as a function of altitude is given in the left side, whereas in the right side you can see that so this mass spectrum here shows that 44 peak, that is having the higher abundance of CO2 in the Martian atmosphere. So this is for chase 1, whereas for chase 2 in Chandrayaan 2, what it here we have employed this is not a impact probe, this is a orbiting probe around the moon. So here in the initial studies we found out that there is a presence of argon. So what argon is happening is that as a function of time, if you see the partial pressure from which you can find out the percentage of argon, here you see that in the first dusk up to dusk you have a abundant presence of argon. In the night side this argon is coming less, that means it is coming back, that means it is freezing. So again, after dawn, you can see that rays in the argon presence. That means in the sun during the daytime, the argon is present, but during the night time it is freezing due to the low temperatures of that particular atmosphere. And again, it is getting released when it is coming to the daylight. This was found. Whereas in the MAM machine, we have used MENCA, which is also a quarter pole detector. So, but it has a mass range of 1 to 300 AMU. So here it has a provision of to track time variation of that particular mass species also. That means in particular time, what is the elements are present as a function of day also, you can find out what is the species are present. So here, this is a MENCA. So this is the this is the Mars orbiter machine where you can see that the satellite will be this. You see that this rectangle right labeled with red color having our MENCA, that is the mass probe. So which is placed in the spectrometer in this mass probe, where you have found out, we have found that what is the percentage of argon as a function of altitude at different day times. So what is the final take home message from these machines is that, so we have used the mostly we have found out the presence of presence of water and presence of argon, as well as high dominance of CO2 in the moon, as well as presence of argon in the Mars, with the mostly from mass spectrometer, which will be supported by other spectrometers. So what is the difference between these three machines is that, so the observation platform for Chandrayaan-1 is impacted. That means while impacting, what is the atmospheric composition, it has found out from 100 kilometers till it impacts to the moon. The second one is the orbiter machine, as well as this moon machine is also orbiter machine. So as we need to telecommand the impactor machine, it is not a telecommand enabled, whereas Chandrayaan-2 as well as MAM machine mass spectrometer is telecommand enabled. Whereas the mass range for the test one, that is Chandrayaan machine is 1 to 100 AMU, whereas for Chandrayaan-2 and mass machine is 1 to 300 AMU for this mass spectrometer. The resolution is 1 AMU for and 1 each for Chandrayaan, Chase 1 and MENCA, whereas for Chandrayaan-2 this is Chase having 0.5 AMU resolution. For all the cases, mass analyzer uses quarter pole detector, quarter pole analyzer. So this is the basics. I won't be indulging interpretation. I won't be telling in depth. So this is the basic overview of the spectroscopic techniques that we have touched for launch vehicle systems for identification and quantification of different materials and qualification of different materials, as well as in the machines for Mars and Moon. What are the major payloads that can be used? Different spectrometers that can be used. So what we have used, mostly we have used is a mass spectrometer, which have validated with IR imaging spectrometer also. Thank you.
Thank you, Srinivas sir. Participants, this is the time for questions. If you have any question, please post in the chat box. Any questions about the session? Sir, we have one. I got one question, sir. What metals are used for space shuttle thermal protection systems? What metals are used for space shuttle thermal protection systems?
Yeah, this is silicon-based adhesives only. Silicon-based adhesives. So
Okay.
which will be painting over the.
Okay, painting, silicon painting. Okay, sir. Next, second question, sir. How sampling is done while spectral analysis on Moon?
So that's why I told. No? So we will be having a telecommand.
Okay, telecommand. Okay, sir.
So for other two machines, we will be having a telecommand placed at different places of our India. So we will be taking the data. So that will be analyzed. So
Okay.
especially our SPL will be doing that only, Space Physics Laboratory, which is situated in Trivandrum.
Oh, okay, sir. So third question, which spectroscopic techniques are used in identifying the living things extraterrestrial,
Yeah.
extraterrestrials?
Yeah, as I told you, so there will be different spectroscopic methods. So it's not a single one. So you will be having a XRD will be there. So it will be having a XRF and NMR spectroscopy. So it will be combination of spectroscopy where you can for it's not a single spectroscopy that will be used. So depending on the type of system, let us say that if it is a inorganic system, you will be going for ICP-MS or ICP-AES system. Okay, if it is
Oh,
organic kind of thing, you will be having a R this GCMS, or you will be extracting that. If it is organic residue is there, so you will be extracting that in particular solvent. So you will be adding different solvent to extract the organic residue, and you will be doing this IR, GCMS and NMR spectroscopy. If it is not soluble, means we will be going for solid state or XRD spectroscopy. XRD.
okay, sir. Thank you, sir.
I have one question.
Yeah.
Sir, we have this Hubble telescope, and
Yes.
recently there was this James Webb telescope which was launched into space,
Yeah. Yeah.
December 2021.
Yes.
Why? When ISRO is going to launch such space telescopes?
As of now, we are interested in the direct means we will be as of now we are developing payloads only, because we want to have a better quantity, because we are the persons who quantitatively told what is the means directly evidence the water in the moon, as well as the abundance of CO2. So we will be mostly interested either mostly for the payloads only. That means we will be taking particular spectrometer or something to there and to find out to measure a particular component. So now Chandrayaan 3 also we are planning. So and Adhitya mission also in future we are planning. So we are mostly interested in payloads as well as the re-entry of the launch vehicle, so that we can take the human being to particular place. So mostly we are dealing with these things.
So another question, sir. What is the purpose of solar cell adhesive?
Because so actually the satellite, let us use it will be having a batteries, correct? So how it will be powered? So it will be having a particular lifetime. If you are at a home, you can recharge it, but at space you don't have that provision. So what is the requirement of solar cell adhesive means? So you will be having a, so here you will be spacecraft will be it is compact. When you go there, so it will be deploying its solar panels, correct? So to that solar panels to be stick to the your particular part of that spacecraft.
Okay.
To for adhesive purpose only we will be using this solar cells to be attached to the your particular spacecraft.
Okay. Okay,
Solar
sir.
cell adhesives will be used because so that it can be continuously working for several years. Let us say that now the spacecrafts will be used like at least 5 to 10 years. So you cannot have that much battery power without any sunlight. So you will be taking the advantage of sunlight to convert into your chemical. It will be storing so that that can be used to orbit to a particular planet. Let us say that it's moon or Martian or any extraterrestrial planet, you will be use that to revolve around the orbit, or to if it is coming to that gravitational force, it should pull back so that
Okay.
it should come to we have to raise that orbit so that the gravitational pull it has to withstand. So these things for these batteries are required to
Okay.
have.
Okay.
I also have yet another question.
Yeah.
Sir, mankind has been deploying so many spacecrafts,
Yeah.
satellites into the space. So
Yeah.
we are not leaving the space also, and we are polluting that place also. So
No, no.
how
Now,
how are these organizations trying to clean up that space?
now only this came because especially this LEO, low Earth orbit. So all the satellites we are keeping there, especially for imaging purpose or for communication purpose or for remote sensing have to map particular thing. So many debris are being formed. So nobody is taking care. Now it's almost this low Earth orbit is continuously. So many things are there. So now only this to remove that debris only now so many proposals are coming. So at some point it will come that so to use the space your debris whatever are there you should eliminate. You should remove that. Like that some mechanism will come soon because already so many works are going on to how to eliminate those debris. There are two possibilities. Either you have to kick off the debris so that it should go to the extra solar system so that it won't interfere our this satellites, or you have to deorbit so that it should particularly you have to make it fall in particular ocean so that it should not impact any particular region. So these two possibilities people are exploring and which will be soon coming also at some point.
Thank you, sir. Thank you for your information. I would like to call Beverly for the vote of thanks.
I, Mrs. Beverly, Faculty Department of Chemistry, on behalf of Department of Chemistry, would like to sincerely thank you for your sincerely thank you for sparing us your time and sharing us your valuable experience and insights. Thank you, sir.
You're welcome.
Last but not the least, I also thank my colleagues for their efforts in making this event a success. I thank you once again, one and all.
Thank you very much, Beverly, for the vote of thanks. I have a request to all the participants to kindly switch on their videos so that we can take a photograph along with the esteemed speaker of today's session. I request Vidita ma'am to kindly take a snapshot. I request everyone to kindly switch on their videos. Vidita ma'am.
Ramya, I think sir should stop presenting the screen, I guess, sharing the screen.
Okay.
Yes, ma'am. One more minute, please. Yes, ma'am. Thank you all.
Thank you, ma'am. There's also a small instruction for the participants. The feedback form for day one of this webinar was already posted in the chat box. I request all the participants to kindly give your valuable feedback for today's session. The session will be live for next 5 more minutes. Kindly, please give your valuable feedback. With this, we come to the end of day 1 of the webinar, Spectroscopy, the fascinating science of structure determination. Hope to see you all tomorrow again. Have a good evening. Thank you one and all once again.
Thank you, Ramya. Can we leave now?
Tomorrow we have yet another session on spectroscopy and its application for structure determination in a regular chemistry research lab. Which all techniques are we going to use for structure determination? We'll have a talk on that. Thank you everyone for joining. Hoping to see you all again tomorrow.